Guys, welcome back to my system design series. If you are new to this playlist or new to this video, then we are covering DDIA book of system design. Up till now, we have completed up to chapter number 6 and we have also started chapter number 7, that is a transaction. In this video, we are continuing chapter number 7 and we will cover serializability in database transactions, concurrent schedules and isolation levels, actual serial execution, challenges of serial execution, stored procedures versus interactive transactions, scaling with partitioning, and pros and cons of it. Also, make sure you watch at 1.5x or 2x for better experience. Okay, so let's get started. Our topic is serializability in database transaction. In databases, serializability means that even if transactions run at the same time, the end result is same as if they had run one after another. This prevents race conditions, conflicts where overlapping the operations can corrupt the data. For example, lost update occurs if two transactions interleave. One transaction reads the balance before the transaction 2 commits its deposit and then overwrites the new balance. Let's understand this by taking an example. Suppose there is two person, Alice and Bob. There is an account as of now having the $0. Here, Alice was trying to deposit some amount in the account, but meanwhile, Bob is reading this balance and Alice commits its transaction, but at the same time, Bob also commits the transaction. So the Bob is overwriting the Alice's deposit. So for example, Alice was trying to deposit $20 and Bob was depositing $30. So instead of the account to be having $50, it is just overwriting $20 with $30. So inside this, there is a $30. So here, by contrast, serial execution, that is a one transaction at a time, avoids this whole situation. So each transaction T1 and T2, sees the consistent state left by the previous one, so no updates gets lost. In other words, serializability ensures the effect of concurrent transactions or actions is as if they happen in some sequential order. Okay, so here concurrent schedules are organized by isolation levels, and the NCSQL standards defines four levels from weakest to the strongest. So those four are read committed, repeatable read, snapshot isolation, and serializable. So here in read committed, a transaction can only seize the data committed by others. It avoids dirty read. However, if it reads same row twice, if it reads same row twice, the values might change in between. That means it is a non-repeatable read. We have already discussed all of these topics in the previous video, but we are doing a quick revision of it. Okay, so let's move towards the second one, that is a repeatable read. It ensures that once the row is read, okay, let me write with different color. Yeah. Ensures that if the row is read, repeated reads sees the same value. Now, this fixes the non-repeatable reads issue, but the new rows matching the same query still appears. For example, if you are selecting that select star from the cities. So before it was just showing the two rows, but now again after some time, if you make the same query, you are able to see another row. That means now instead of two, you are able to see three rows. So that means your values are not getting changed, but some of the rows might be added, some of the rows might be deleted. Okay, so let's move towards the next one, that is a snapshot isolation, MVCC. In this, each transaction works on the private snapshot of the database. Now, this avoids most of the anomalies with good performance, but subtle issues like write skew can still occurs. That is, two transactions update different part of the constraint in a way that only a serial order would have coded. That is, suppose there is a common shared document and T1 is just updating the bottom part of the document and T2 is trying to update the top part of the document. Okay. So let's move towards the next one, that is a serializable. Now, this is the strongest level. In these, transactions are completely isolated. That is, they are having effectively serialized access. All the anomalies such as dirty reads, non-repeatable reads, and phantom, etc. are prevented by definition. Okay. So that means only serializable isolation fully guarantees correctness. The outcome is exactly like some serial, that is one at a time execution. This eliminates all the race conditions. In practice, many databases use weaker levels by default for performance, only using serializable when strict accuracy is required. So that means most of the database are still using the weaker isolation level as by default. But if they need it, they will go for the serializable isolation. Okay, so now let's talk about actual serial execution, that is a one transaction at a time. A simple way to achieve serializability is to never overlap transactions at all. In actual serial execution, the system runs each transaction from start to finish before beginning the next one. Okay, to understand that, let's take this example. There is a one vending machine, and each vending machine or a one single vending machine serves to only one customer at a time. And in the same way, a serial execution model processes transaction A fully and then starts with the transaction B. Now, this guarantees the consistency because no two transactions ever interfere. Okay. Early on, this idea was impractical, but modern systems have made it viable. For example, around 2007, in-memory databases like WorldDB and the use of cheap RAM allowed entire datasets to stay in memory, so each transaction ran extremely fast without I/O. In fact, some of the technologies are inherently single-threaded, such as JavaScript or Node.js, are designed for it. Systems such as WorldDB, Redis, Datomic have adopted this model, and by eliminating locks and coordination entirely, a single threaded engine can sometimes outperform a classic multi threaded databases on a single core. Every transaction runs alone, so there are no race conditions by construction. Okay, for this, imagine there is a single cash register in the store. If one customer is paying, every other customer forms a queue. Now, here, each cashier interaction is a transaction, and only one person is at the register at a time. No two customers can accidentally merge their payments or purchases. Now, similarly, serial TVs perform the transactions one by one. So, the before and the after states are always well defined. Okay, so now let's move forward. Let's talk about the challenges of serial execution. Okay, first is waiting time. Here, if suppose one transaction takes long time because of the complex logic or slow IO, all the remaining other transactions wait in the queue, and this can increase latency for others. Next one is single core limit. Since by design only one transaction can run at a partition, throughput is limited by single CPU core speed. So because of this, overall system speed suffers with more serial work. Next is memory requirement. To be fast, Serial Engine keeps the entire worksheet or work set in RAM and avoid disk. And if the data doesn't fit in the memory, performance degrade significantly. So this system sacrifices conventional parallelism. They restrict throughput to one core per partition because there are no locks or latches. A well optimized serial engine can reach very high transaction per second on that particular code. Okay. So our next topic is stored procedures versus interactive transactions. Okay. Now, because transactions can't wait on external input or network round trips, serial databases require the entire transaction logic upfront. That is, it should be in the RAM. So, in other words, you package the transaction as a single store procedure or single programmatic call on the server. Traditional multi-step transactions, for example, show lights to users, out of which users picks one and they update seats and so on. All of these multi-step transactions involve long pauses for user input. Now, in serial database, this is impractical. The system can't idle halfway through one transaction without blocking others. Instead, every transaction or everything must happen at once in the memory. Let's understand this by taking an example. Suppose you are using Make My Trip to book a flight. A serial engine will run one stored procedure that checks the seat availability and updates the seat inventory in one go. Now, what is stored procedure? A stored procedure is pre-written saved block of SQL code that you store in the database and you can call it anytime to perform in the database to perform any specific task. Okay. Now, doing multiple back and forth queries would be so companies like VaultDB and Atomic requires you to write transactions as a stored procedure in the languages on the server side. Modern systems often let you to use familiar languages. For example, VaultDB supports Java or Groovy. Redis scripts uses Lua. Atomic uses Clojure, etc. This avoids vendor-specific SQL dialects. Here, the upside is speed. No network or I/O inside the transaction. That means it runs very fast. Now, the downside is the application's logic must be moved to the database and be fully known ahead of the time. So, both we have discussed upside and downside. Let's move forward. Let's talk about the scaling with partitioning. To overcome the single core bottleneck, serial databases often partition the data and workload. Each partition is a separate thread, single threaded engine handling this own slice of data. Let's understand this by taking an example. Suppose there is a wall DB. It divides this table into multiple partitions or sites on one or more machines. Suppose these two both are the part of the single machine. Now, if a stored procedure only needs the data from one partition, this is partition and this is machine. Suppose this is having partition 3 and 4 and machine 3. Okay. So, if a stored procedure needs the data from only one partition, that partition thread can perform or processes it independently, allowing other partitions to work on different transactions parallelly. So, because of this, you get the linear scaling. That is, more CPU cores or partitions means more transactions per second as long as the transaction stays in the same partition. However, if a transaction must touch multiple partitions, that is a cross partition transaction, extra coordination is needed. So in this, typically one node act as a coordinator and it splits, suppose this is the work, into multiple partitions, splitting the work to each partitions, and then it combines the result of each partitions. Combine results of each partition. Now, this coordination adds latency and overhead. In practice, cross partitions writes are much slower than single partition. Therefore, careful database design is much needed. Choose partition key so that most transactions stays within one shard. If that is achieved, the system will scale linearly. And if not, you pay a performance penalty for distributed systems. Okay, now let's talk about pros and cons of using serializability. The pros are serializability guarantees correctness. A true serial schedule has no concurrency bugs. By running single threaded, you avoid locks and can get very deterministic performance. Well partitioned workloads can almost scale linearly with the number of partitions. Systems like VaultDB report high throughput when data access is partition local. Okay, now let's talk about the cons. The biggest drawback is limited concurrency. You are capped at one CPU, 4 per partition. Slow transactions delays everyone and workloads must fit in the memory. Also, you lose the convenience of multi-step interactive transactions. All logic must be stored in the stored procedure. Cross-partition transactions can be worked, but it is more expensive. In other words, you trade ease of scaling and interaction for simplicity of consistency. In practice, system using actual serial execution such as VaultDB, Redis, etc. succeed in low latency, high throughput scenarios where transactions are short and data can be partitioned. They provide rock solid serializable model eliminating the race condition by design. But they require thinking differently about application design using stored procedures and partitioning data upfront. So, serializable isolation via actual serial execution is the safest way to avoid concurrency anomalies at the cost of above challenges. Those are using stored procedures and partitioning data upfront. So I hope you have understood all the topics. If you are still watching this video, then please make sure to subscribe to my channel and like this video and comment down if you have any doubts. Thank you so much for watching.